Okay, hello, and this is just a short tutorial on how to do a basic calibration of a camera, in this case a web camera in MATLAB, and also acquire an image of an object and then perform some measurements on that object, which we actually will kind of call a blob at this point, but you'll see what object it is in just a minute. So the first thing we have to do is calibrate the camera like we did previously. So I'm going to type in the iMac, and we're going to capture a calibration image using the iMac tool. And we want to use a resolution of 1280 by 960 if we can. If you don't have that resolution, try and get as close as you can. And I'm going to start the preview at this point, and we'll see what's happening. So here's what we have. Here's the computer, and I have a piece of paper, and you probably have to use a webcam that's wired like this one, so that so that you can point it at something. It make life a lot easier. So what we want to do is fill the webcam image with the page where I've drawn lines. Now these lines are just very sloppily drawn. They don't have to be perfect, but you do want to use a ballpoint pen because that's about the right width. And I'm now going to set parameters for the camera. And this is really important. You need to have your frames per trigger to be 1 frame. We're just going to capture 1 frame. But we do want the color space to be RGB because our camera is probably RGB camera. And we'll look at the device properties. We have, right now I have it on auto exposure mode, and I'm just going to leave it on auto, and you can do that, and hopefully it'll come out good enough for you to get a basic calibration. And so you can see what the default values are for my camera, and you can change them. You can change the values for your camera to make a better image. For instance, I'll just go ahead and change the brightness here a little bit, and we'll brighten up this image, and I think that's a good idea. Okay, so now we're going to capture the image with Start Acquisition. Okay, I just captured the image, and make sure that you've captured it such that it fills the whole frame. You don't have like black, or you don't have a border, so make sure you get that. Alright, now this came in a little blurry, but I think it's going to work anyway. So now we're going to export the data. I'm going to set the webcam down. We're going to export the data. We're going to export it right into the workspace, and we're going to call it calib. And that's the name of our image. So here's our calibration image. And now we're going to go ahead and we're going to close that. Let's these are just warnings. It's not, doesn't cause a problem. I'm going to type CLC, clear everything, and clear the command window that is. And now we're going to take a look at this calibration image and make sure that it looks reasonable. So, okay, so it's blurry, but I still think it will work. Hopefully yours will be a little bit clearer than this. But I've captured the lines and the hand-drawn lines, and you can see a little bit of distortion effect. Okay, so now what we're going to do is we're going to try and calculate the lens parameters using the lens params _mat program. And I'm going to change this to just calib. I am calib. So that's my calibration image, just the basic image. And let's see what happens. Okay, it doesn't look like it worked. What happened? It looks like it didn't capture any images because this image is completely gray, so there's no edges. So that means we might have to do something to this picture to make it easier for the program to capture the edges. So let's go ahead and try let's try this little trick, which is to use the HisDQ, and let's see what that looks like. Now, I can't just HisDQ calib. Let's give it a try. I'll show you. We'll see what happens here. I'll show you what happens actually. So, if I take and I try to do just a HisDQ of calib itself, calib is a RGB image, and HisDQ doesn't really like RGB images. so it gives us an error. It wants it to be two-dimensional. So okay, so we have to convert this to a grayscale image. So let's call it calib equals, and then I'll just copy this. Well, I could just do it this way. Calib equals RGB to gray calib. Okay, so that worked. And now we're going to type EQ calib equals hist EQ calib. All right. So now we have that. Let's show it. Let's view it. I am show EQ calib this time. Aha, so we got a very dark image. This is going to be difficult to calibrate from, but we'll give it a try anyway. We've got a lot of shadowing here. You try to avoid the shadows if you can. So let's go ahead, but let's see if it works anyway. I want, instead of calib, I want to be calibrating EQ calib. Okay. Well, it looks like we found some edges, and it looks like the optimization is working, because the edges look like they're straight. You saw how it was very convex. Okay, great. So it looks like we got excellent lens parameters, and it's now performing a correction, and we're done. Okay, so now you see the lines are all pretty straight. So it worked pretty good, even with this terrible shadow. So I'm sure you can get it better than this. Okay, so now we have our calibrated, and these are the edges that were detected. So it focused on the lines, obviously. And we are ready now to capture the image of the object that we want to measure the shape of. So I'm going to go ahead and put a white piece of paper down, and I'm going to capture an object. And here's the object that I want you to capture. I have one, so I'm going to start with the iMac tool again. And we're going to start the preview again. And here's the image that I want you to capture. Here's the object that I want you to determine properties, shape properties of. So this is obviously, it's a remote control. So I'm going to hold the camera at the same distance that I held the camera when I calibrated. So it was about, I think about 9 inches is how far away my camera is from this remote control. And I'm going to start the acquisition and capture one frame. Okay, and it's still a little blurry. I can't seem to get my camera to be perfectly in focus, but it'll do for the purposes of this example. So now we're going to export the data. This time we're going to call it something else. We'll call it remote 1, just in case. Okay, so now we have that. And we'll close this window. CLC again to get rid of the warnings. You can also type warnings off, and that will, warning off, and that will turn off those warnings. Okay, so now let's take a look at the remote image. Show remote 1. Okay, this is a little blurry, but I believe this will work fine. What we're trying to do is we want to calculate the area, the length of this object, and the width of the object, and also we'd like to calculate the perimeter and maybe some other geometric properties of this object. So we're going to measure these things using the image. Alright, let's go back for a second and go back to the calib image, and I'm going to type show calib again. And what we want to do first is we just need to get our pixel per millimeter ratio, calibration ratio. So let's go ahead and, let's say millimeters per pixel. And since I've marked a 10 millimeter gap here, or length here, we're going to just go to Tools, go to the data cursor, like this, and we're going to left click, on that. Then I'm going to right click on this box and I'm going to export cursor data to Workspace. And I'm going to call this line 1. Okay? Now, I'm going to click here on the other line, one that's a bit to the right. And now I'm going to right click here and I'm going to export cursor data to Workspace. I'm going to call that line 2. Okay. Now I'm going to close this window. And I see now in my Workspace I have 2 structures. These are structures, okay? And if I double click on that, I see what's inside the structure is the target, which is the gray level, and then also the position, which is the location in row and column of the cursor, or whatever the pixel that was under the cursor. So now what we're just going to do very simply is close this. Well, for instance, if I type line 2 position, I will see that I have the position values from the structure. So let's go ahead and calculate the difference between line 1 and line 2. And we get 2 values. The x value is the rows, so that is 63 pixels per 10 millimeters. So that means 63 divided by 10 millimeters, 6.3 millimeters per pixel. So there's my calibration, and you can just save that for later. So you have the diff calculation here. Okay, so now it's time to go ahead and threshold our image and do a few morphological changes or filters in order to be able to perform some calculations. Okay. Okay, now we go ahead and we un-distort the remote captured image that we just captured. So let's go to the command on. Okay, I have this saved already, the command, and it's called, we'll call the image result C for corrected remote, C remote, and then the image we want to correct is IM remote 1, and so now we'll go ahead and correct it. It takes some time, so you have to be a little bit patient, maybe a minute or so. I'm going to pause the video until it's done. Okay, that's done. Let's take a look at it. I mean, it probably looks the same to the eye, but we will view it anyway. See remote, just to make sure it's still the kind of image we're going to be needing. And yes, okay, so you can see how it was corrected, and the image was actually pincushioned a little bit to correct for the barrel distortion. And so now what we're going to do is threshold and identify this region. So let's go ahead and do that now. And the very first thing we can try is a simple thresholding. So we'll call this T, or how about IMT, because I already have this variable. So we'll call it image. IMT means image threshold. We're going to use the command IM to black and white, which is just converting it to a black and white image with a threshold value. And this will start out by selecting 0.5, which is in the middle of the scale of the image. So this number ranges from 0 to 1. And we want to threshold this image, C remote negative 0.5, and then let's go ahead and view that. IM show IMT and see what it looks like. Okay, this looks pretty good. So what we have is we have the object, which is now black because of the thresholding, and anything that is light is turned white. So we've thresholded right in between. But we've got a couple issues that we have to deal with. One is that we've got black out here. We want it to be all white. So what can we do with this? Well, it's very simple. We'll just crop this image, okay? Now how do we do that? There we go. I'll show you. It's very simple. All we do is create a new image. So we'll say im crop that is the internal rectangle of the current image. So the current image is called IMT, and what do we want? We want to crop the outer boundaries. So IMT from 20, let's say 10 pixels, from let's say 20 pixels to the end minus 20. That's the rows, and then we'll do the same for the columns. 20 pixels to end minus 20. Okay, and now we should end up with a new image called im crop, and we should be able to view that. Im show im crop. Aha, good. So we've gotten rid of all of these external boundaries. Now we have another problem. Well, what about all these buttons? I mean, they're like holes inside of this image. Well, there are commands in order, because we want to find the area of the remote. We don't care about the buttons for now, maybe later. So what are we going to do? Well, we might be able to fill these with a command from MATLAB. Now, another thing to recall, though, is that this is a binary image. The black is zeros, the whites are ones. We want the remote to be ones and the background to be zero. So we have to complement the image. So I'm going to type im comp equals im complement of im crop. Okay, now if we type im show im comp, whoops, oh, the figure's already open, I didn't close it. There we go. Oh, look, this is great. Now we've got a white remote, which is a blob. If we think of it as a blob, that's what this is called. Blob analysis, in fact. And the background is black. Okay, so we're on the road. All we have to do now is fill in those buttons. Well, that's easy. Let's call it im parim. Well, we wanted to call it im fill, but that's the name of the command. So I'm just going to call that this im f processed. I'm just picking a name here. im fill is the name of the can. I think it's im fill. I'm gonna have to check. Yes, the name of the command is im fill, and we want to fill the im complement image, and we want to fill the holes. Okay, so there we go. So now what do we have? Let's type im show again, and let's see what the result of im fill p. I should have made it imfh probably, but oh, this looks fantastic. So now we have all of the remote is one, the rest is all background. Now the easiest way to find the area, well, let's just count pixels. Let's call it our area equals sum of IMFP. Aha, so what's our area? What is the value? It looks like oh, I forgot. It sums up, I have to type sum of sum. So our area is the sum of the sum, because it does rows and then columns. Sum of IMFP. Okay, so now our area, here it is, 182,602 pixels. So now from this number, you should be able to calculate from your calibration of 6.3, and mine it was 6.3 millimeters per pixel. You should be able to calculate the area of the object. We can also calculate the lengths, very simply by showing the image. So let's go show IMFP again. And let's take a look at that area. And we can use the tools just like we used before. Data cursor to identify key points, calculate their positions, and then we can calculate other things. But it's very difficult physically to calculate what about the perimeter? How are we going to calculate that? Well, one way to do that is to use the BW perim command. So let's call it R or IMF perim equals BW PER perim of IMFP. And we want an 8-fold connectivity. That means that anything that's connected to the perimeter becomes the perimeter. There are other connectivities. You can read about that in the MATLAB manual. Okay, so let's show that. IM show again. IMF perim. And let's see what it looks like. I'm guessing that it's going to, oh, it looks like the perimeter. Okay, but an interesting thing is it didn't show the entire perimeter. It didn't calculate the full perimeter, which is somewhat unusual. So let's go ahead and try it with a 4-level connectivity and see what that looks like. Yeah, it still didn't establish the perimeter, which is extremely unusual. I've never seen that happen before. Well, let's analyze this and see what happened. Okay, well, it turns out that it just looks like it didn't calculate some of the perimeter, when in fact, if you zoom in to the image, you can see that it actually does determine the, in fact, perimeter of this object. Now, it's not a perfect calculation. In other words, there may be some pixels that are doubled up on the perimeter. So you have to kind of be careful about this calculation, but at least if you sum this, it'll give you some idea of what the perimeter is of this object. Now, there is another even better way to perform this calculation, and that is by using the really nice property calculation tools in MATLAB. So let's go ahead and find those. It would be under, let's see, where did I do that? We want to use, excuse this short delay, this region props command. So I'm going to calculate all of the region properties of this blob, and we'll call it imstats, region properties, and IMF, I'm sorry, IM calib, all right, sorry, okay. Wow, I hit the wrong key. Okay, we want to calculate the region properties of IMFP, and we want to calculate all of them. So now I've got all of these statistics or calculations in this. What is it? It is a structure once again. If I double click on this, I can see the form of the structure. Whatever it contains is on the left. So here's the area of this region. Now, of course, this is all in pixel value, so pixel coordinates. We have to convert them using our millimeter to pixel in order to get geometric dimensions of the object. But once you have all of these properties, for instance, the area is here, the centroid is here, the bounding box, which means if you drew a box, what would surround the object, it tells you the major axis length. So this is the length of our object, and this is the width, 723 pixels, 632 or 332. So in my case, the length of the remote is, we'll call it imstats dot major, and if I hit tab, it'll complete that for me. Major axis length, that's my property, divided by 6.3. And that equals 114 millimeters. So, just for the heck of it, let's go ahead and get the caliper and see what the caliper says. The caliper says that the object is, now let's take a picture of that. This is about the best measurement I can get fairly easily of the object. So we'll go ahead and put that on video for you to take a look at. I am a cube tool. Let's start the preview, and you'll get a chance to take a look at what I've done here. And as you can see from the measurement, well, it's a little hard to see. I did the best I could, but caliper says it's about 113 in size. Okay, I'm going to stop the preview. That's pretty close to our actual measurement of the major axis length of 114 millimeters. So we're not sure which one's more accurate. We'd have to do a far more accurate calibration with some more precise lines and stuff to make sure that we're really in precise calibration. But this is perfectly good enough for this example. And now the rest of it, of the assignment, is your job. Let's find some more interesting information about our remote control object. All right, that's it for now.